This is a fully produced, multi-act sci-fi radio drama. Every file in this production, from character dialogue to spatial audio, was generated without human intervention. The system responsible is Comfyui Old-Time Radio, or OTR. It functions as an autonomous, headless AI agent operating entirely within a node-based visual interface. As you can see on this cover of Nature magazine, the pipeline grounds its narratives in actual science. It automatically fetches and parses real scientific headlines via RSS feeds to seed the story. From that single input, it manages multi-act script generation, director-level voice casting, Bark-driven text-to-speech, and final spatial mastering. Stringing these steps together using cloud-based APIs with unlimited compute is a relatively trivial task. Executing them entirely on local consumer hardware introduces severe architectural friction. The primary constraint is physical memory. The entire dense, multimodal sequence must execute sequentially on a single GPU capped at 16 gigabytes of VRAM. The exact bottleneck is clear on this capacity gauge. A Gemma 4 model takes 8 gigabytes of VRAM. Stack Bark's acoustic models on top, and you hit the hardware ceiling. If they overlap during execution, weights exceed memory, instantly throwing a CUDA out-of-memory error. Stable local AI requires explicit PyTorch memory choreography and strict system-level boundary hardening to survive runtime. The first boundary to harden is the data handoff. The unreliability of LLMs challenges us when creative text must drive deterministic Python code. The pipeline's format requires explicit structural tags, like this voice tag, to pass through the rigid Python parsing layer. However, the model frequently drops the name field. Incoming text often includes only gender or age descriptors, slipping through the parsing gate without a valid identifier. Because the downstream code hashes that field to assign a specific voice profile, treating words like male or young as the character's name destroys audio consistency across the scene. The initial fix happens in the prompt layer. The system enforces explicit right and wrong format callouts in the system prompt and locks the director node to a strict JSON schema for voice casting. The ultimate fallback is a hardened parser that detects gender words used incorrectly, intercepts the flawed text, and forcibly injects a positional identifier so generation can continue. The second major boundary challenge is factual integrity. The language model often invents plausible but fabricated academic citations and archive IDs to match the script's tone. Prompting against hallucinations is unreliable. Instead, an active post-generation scanner runs a regex pattern across the script. When it detects an archive ID, it cross-references the original RSS text. Finding no match, it flags the hallucination and triggers a systemic warning. Language models require encapsulation within aggressive, fallback-aware programmatic wrappers because they cannot be trusted to self-regulate their formatting or factual output. Managing the data is only half the problem. Standard Hugging Face model loading defaults fail in dense, multimodal pipelines on constrained hardware. This chart tracks VRAM. As Gemma generation concludes, memory flatlines near the 16 gigabyte ceiling. The pipeline pauses. Manually calling unload severs language model references. Garbage collection sweeps them, and usage drops. Emptying the CUDA cache clears reserved space, permitting heavy Bark text-to-speech models to load. Even with this incredibly strict memory swap, an upstream dependency error inside Bark causes the pipeline to generate silent audio. Fixing the underlying allocation error requires deep-level system oversight. The issue stems from specific C-level PyTorch calls inside Bark's semantic loop, defaulting to the CPU. Internal tensor instantiations lack a target device argument. Because of this omission, those tensors are routed to the central processor, while the model weights correctly reside on the graphics card. We can visualize the resulting crash here. A red CPU-allocated tensor attempts to perform an index lookup on embeddings stored in green CUDA memory, triggering a disconnect error. Standard Python context managers and default device settings fail to intercept these operations because they occur at a deeper architectural layer. The solution is a custom, recursive monkey patch. It forcibly intercepts the processor's output dictionaries and manually routes every nested tensor to the correct CUDA device. Running complex third-party models locally requires surgical monkey patching and explicit garbage collection to force compliance with local device mappings. Once the models are safely loaded into memory, the acoustic generation stage faces its own data hazards. Untethered language model creativity regularly contaminates the text-to-speech data stream. Looking at this digital script, raw text generation often embeds unsupported stage directions, like the bracketed words whispers and shouts, directly into the dialogue lines. Bark only supports 13 specific performance tokens. If you pass unsupported stage directions verbatim, the acoustic model breaks and speaks the literal bracketed words instead of performing the intended emotion. To fix this, a dedicated cleaning function strips away all structural tags and whitelists the remaining text against that exact 13-token set, dropping anything the system cannot accurately render. Beyond managing data internally, the system has to report its status. A long-running, headless pipeline running intensive calculations will appear completely frozen to the human operator. This diagram shows the monitoring architecture. 3 parallel daemon threads, logtailor, WebSocket, and heartbeat, run continuously. The heartbeat stream taps the generation function, extracting token-per-second metrics. To prevent file corruption, these threads converge updates using atomic writes, creating a solid JSON output dashboard. Resilient automated pipelines must simultaneously sanitize their internal data flow while constantly exposing their internal state to external watchdogs. This topological view traces the entire automated journey across the 12-node pipeline, from a raw RSS headline to a fully mastered audio file. Building tools like this exposes a core engineering reality. The integration of fragmented systems now presents the primary hurdle in local AI development, surpassing the raw capability of individual models. Stable local agents require treating language models as untrusted input streams. Their outputs must be rigorously filtered, constrained, and formatted before touching downstream code. Furthermore, developers must aggressively dominate hardware memory states rather than relying on the passive execution frameworks designed for isolated testing. Achieving this broadcast aesthetic through an autonomous pipeline represents a deep-level engineering challenge. By combining strict boundary enforcement and explicit memory choreography, a standard visual node interface is successfully transformed into a robust, completely headless production environment.